To a brand new unit of study talking about historical quadratic functions, which we've seen before, and applications of those quadratic. We've already talked about quadratic functions sort of extensively. We've solved some quadratic equations, and we've graphed some quadratic functions back when we did transformations of graphs. So we've seen a lot of quadratic formulas, a lot of quadratic equations in this form that's highlighted here. The f of x equals ax squared plus bx plus c. We've seen a lot of them in that form, that standard form. And the parent function, we know from the transformations lesson, is f of x equals x squared. That's your parent function for a quadratic. There's a new form that we're going to see this lesson, and that is vertex form. And this is what vertex form of a quadratic looks like. You can write any quadratic in standard form, and you can write any quadratic in vertex form. They both have sort of their own benefits and drawbacks, right? Vertex form, the benefit of it is that it's written as if you were going to graph it like a transformation. So if you remember back to the transformations, the plus k will shift it up or down, the minus h will shift it left and right, and the a will consider as a slope, right? It's going to stretch it vertically or shrink it vertically. If the h and k shift it up, down, left, right, then that means that we can make this relation that hk is the vertex of that parabola. If we can get it in vertex form, then hk is the vertex. Notice that that negative sign is built into the formula, x minus h. And so whatever number is in there, we're actually looking at the opposite of that for the vertex. So remember that within a parentheses, when we're talking about transformations, it's going to shift it the opposite way of what you think. So if we had x minus 3, it's actually going to shift it to the right 3, right? And so the vertex is shifted to the right 3. The vertex, like I was saying, that negative is just built into the formula. All right. So within vertex form, there are a couple of other things that we can see. We see obviously the vertex that we were talking about, h, k is the vertex. And then since a we're talking about is our slope, if a is a positive number, the parabola is going to open upwards. So here in this example, a is positive. It opens upward like a cup. If a is less than 0, that means if a is negative, the parabola opens downward right here. The cup would spill out because the parabola is opening downward. Notice that when the parabola opens upward, every time a parabola opens upward, you're going to have a minimum point, right? A lowest point of the graph because the parabola is opening upward. Anytime it's opening downward, you're going to have a maximum point. That maximum or minimum point is your vertex. These points right here that are labeled, those are your vertex. The maximum point of a parabola is a vertex. The minimum point of a parabola would be its vertex if it was opening upwards. That's going to really help us out when we get ready to solve applications, because if we look at something like this, let's just look at the one on the right, for example. If we look at this looks like the arc of, if we just threw a ball, right? If we just threw a ball up in the air, it would take the similar path. And so we could use a formula for an equation of a quadratic and try and figure out how high that ball was going to go, right? The ball would reach a highest point, and that point would be its vertex. We'll see that a little bit later on in this lesson. All right, analyzing the graph of a quadratic function, determine whether this quadratic function f of x opens upward or downward. Since a equals negative 2, this one opens downward. That means that it's going to have this general shape, right? Identify the vertex. That's hk. And remember that x minus h is built into the formula, so that's actually 1, 8. And that makes sense when we think about those transformations, because last unit, when we were talking about transformations, we said that was going to shift you right and up. So the vertex is right 1, up 8. The x-intercepts and y-intercepts, we always do those the same. So to find any x-intercepts, what we do is we sub in a 0 for y. To find any y-intercepts, we sub in a 0 for x. Let's do that. So for the x-intercepts, if we sub in a 0 for y, that'd be 0 equals negative 2, x minus 1 squared plus 8. And then we need to solve for 8. So first we could subtract 8 I said we need to solve for we need to solve for x. We could divide by -2 on both sides. We could take the square root on both sides to get rid of the square, because square and square root are inverses. Remember, anytime you take the square root on both sides, you are going to get a plus or minus with your answer. So then x equals 1 plus or minus 2 once we add 1 to both sides. We could say 1 plus 2 is 3. 1 minus 2 is -1. So those are your two x-intercepts. 3 and -1. Really, those are points, right? And so when I write them out, I'm going to erase this t-chart. Now that we're looking at two x-intercepts, I'm going to erase the t-chart and just write out the values. So my x-intercepts are actually, I plugged in a 0 for y, so that means I have 3, 0, -1, 0. All right, for the y-intercepts, that means we need to sub in a 0 for x. Y equals -2 times 0 plus 1 squared. 0 minus 1, squared. Plus 8. I'm running out of space on that right side. Y equals -2 times 0 minus 1 is -1 squared plus 8. We could sub that into our calculator at this point and get y equals 6. So the y-intercept would be, we plugged a 0 in for x and got 6 out for y. The next part, E, says to sketch the function. Here, let's sketch our function in a different color. So here's what we have. We have our x-intercepts at 3, 0, -1, 0. Our y-intercept at 6, 1, 2, 3, 4, 5, 6. We have our vertex at 1, 8, 1, 8. And I think we have enough points here that we could go on and graph this function, right? We have a good idea of what it's going to look like. We know it's going to open downward, so it's going to look just like this. Here's another feature of these quadratic functions. They always have an axis of symmetry. They're always symmetric right around that vertex. They're perfectly symmetric. And that line is the line x equals 1. It's always going to be x equals and the x coordinate from the vertex. That's always going to be your axis of symmetry. Since the vertex is the highest or the lowest point, it's going to be symmetric around that point. What is the maximum or minimum value of y? Well, that's our vertex right there. Our maximum value is 8, and that occurs at x equals 1. And write the domain and range. For any quadratic, the domain is going to be -infinity to infinity. There's nothing restricting that function. There's no way to square root a negative. There's no way to divide by 0. So the domain of a quadratic is going to be -infinity to infinity. We could also look at how far left it goes, and it does go way left on this graph and way right on this graph, as far as you would want it to, all the way to infinity. The range, on the other hand, if we were looking at the range, here I'll do it in a different color. The range, it'll go down as far as you want it to, right? All the way down to -infinity. That's not the case when you start to go up, though. When you go up this y-axis, the highest it goes is right there at 8. The maximum it goes is up to 8. And it does reach the 8, and so we'll use a square bracket on the range. It's a lot of information we can get from one graph, and that's really going to help us out when we get to the application section of this lesson. All right, here's another. Writing a quadratic in vertex form. Okay, this is sort of a tough process because we have to complete the square to get it into this vertex form. And the way that we do this, the easiest way to do this, is first to start by dividing everything and getting this to be just x squared. So we can divide everything by 3 to make that just a x squared. I'm dividing the right side and dividing the left side. I'm just sort of distributing it through that right side. X squared plus 4x plus 5 over 3. All right, when we're doing completing the square, what we can do is we can shift that 5 over 3 over. 5 over 3. It's going to make things a little bit easier because remember with complete in the square, we're looking at b over 2. So b is 4. b over 2 is 2. b over 2 squared is 4. So what we're going to do here, this is going to be a little bit of a strange process. We're going to add 4 and subtract 4 from this side. So really what we're doing is we're adding a net value, net add 0. We're really adding 0, right? We're adding 4 and subtracting 4. We're really adding 0. This is going to work out in a really special way though. We're doing it on purpose. So what's going to happen here is this part that I have here, that's a perfect square quadratic. We're sort of making this problem, we're formatting it so that it will work in our favor. And if we went and did star method with that section, it would be x plus 2 and x plus 2, which is x plus 2 squared. What we have left over here is 5/3 minus 4. So I can type in my calculator, 5 divided by 3 minus 4, and change that into a nice fraction. That's going to be negative 7 over 3. So I just combine those numbers right there in my calculator to get 7 over 3. We're almost done. All we have to do now is get y by itself. And so to get y by itself, we need to put that 3 back on the other side by multiplying by 3 to everything. So we have y equals 3x plus 2 squared minus 7. I'm multiplying 3 by everything. I don't have to distribute the 3. We have our equation now in vertex form. All right, I would pause the video now, and now that we have it in vertex form, go through and see if you can figure out the rest of this stuff. The vertex is going to be hk, which is negative 2, negative 7. The x-intercepts, we need to sub in a 0 for y, so that would be something like 0 x-intercept. 0 equals 3x plus 2 squared minus 7. I'm afraid this one is not going to work out as nicely as the last one. 7 over 3. Yeah, that's not very nice. We can square root both sides. We have plus or minus 7 over 3, plus or minus square root 7 over 3 equals x plus 2. So then x equals negative 2 plus or minus square root of 7 over 3. Those are our two x-intercepts. Not very nice numbers. The y-intercept, again, we plug in a 0 for x. And that's going to be y equals 3, 0 plus 2 squared minus 7. Y equals 3 times 2 squared minus 7. This one's going to work out a little bit nicer. You can type that in the calculator, and I believe you'll get y equals 5. Sketch the function. We don't have very nice values here, so I'm actually not going to use these. They're just not very nice to graph. But I do know that the y-intercept is 5. 1, 2, 3, 4, 5. I know that the vertex is negative 2, negative 7, negative 1, 2, negative 1, 2, 3, 4, 5, 6, 7. And I do know because this a equals 3 that it opens upwards, and so I'm just going to get a basic sketch here. I know that it opens upwards and it has to go through those points. Man, I'm really missing this graph. That's just going to have to do. The axis of symmetry then is going to be like this, right? And it's going to go through that point right there, which is x equals negative 2. Remember that the axis of symmetry is always x equals the number of your vertex in the x position, because it is going to be through that vertex. That's your maximum value as well. So this right here is your maximum value. That right there, the negative 2, negative 7. So the minimum, I'm sorry, this is a minimum because it's at the bottom. The minimum is negative 7, and that occurs at x equals negative 2. The domain, like I said, is always negative infinity to infinity. And then the range, this time does not go all the way down. It goes down to negative 7 and up to infinity. Down to negative 7 and up to infinity. All right, if we want to just find the vertex, right? If we don't want to go and put it in vertex form, but we still just want to find the vertex, there is a formula for that. Here's the formula, and it looks worse than what it is. And so it's an xy coordinate. It's an xy coordinate where this is your x, and then all you have to do is sub your x back into the formula to find your y. So negative b over 2a will find your x, and if we sub that back into the formula, that'll find the y. So what we could do here to find the vertex, all right, state whether it opens upward or downward. Our first coefficient is negative, and so it's going to be opening downward. Find the vertex, that would be negative b over 2a. That would be negative 4 over 2 times negative 1, which would be a positive 2. To find the y-coordinate, we just need to plug that positive 2 back into our original equation. So that would be something like y equals negative 2 squared. That's negative x squared, I'm sorry. So it would be negative 2 squared plus 4 times 2 minus 5. Solve it now, we get y equals 7. So that's our y-coordinate of this vertex. And we didn't have to get it into vertex form to find that either. Find the x-intercepts, so that'd be 0 equals negative x squared plus 4x plus 5. Remember, anytime you want to find the x-intercepts, you sub a 0 in for y. You can divide everything by negative 1 here just to make your problem look a little nicer. X squared minus 4x plus 5. And then do star method with this and get x minus 5. X plus 1. So then the x-intercepts must be 5 and negative 1. To find the y-intercepts, just like we have been doing, we could just sub a 0 in for x. Y equals negative 0 squared plus 4 times 0 minus 5. So y equals negative 5. Sketch the graph. So we'll sketch all of our points here. We have the x-intercepts at 1, 2, 3, 4, 5, x-intercept at negative 1, a y-intercept at negative 1, 2, 3, 4, 5. We have, what else do we lack here? Our vertex is at 2, 7. Oh man, we messed something up here. Y-intercept is at negative 5. Vertex is at 2, 7. Oh man. I lost a negative sign here. So that would be negative 4. I'm glad we noticed that here. I knew something was going on because our vertex wasn't going to line up with the rest of the problem. Our vertex is actually at negative 1, and our vertex y-coordinate here is at negative 1. If we were on a test, we would have caught that. So our point 2, negative 1. 1, 2, negative 1, right there. That is still not lining up. Vertex, negative b over 2a. The vertex is 2, negative 1. We must have done something else incorrectly. X minus 5, x squared. Oh man, I see it. All right. I've made all sorts of mistakes on this, but I guess this is a learning experience for all of us. It's in the x-intercepts, we need to go backwards a step, backwards another step. Here's where I made the mistake. When I divided everything by negative 1 here to make it look nicer, I put a positive 5. That should be a negative 5. That's totally my mistake. That still gives me x minus 5 and x plus 1. What in the world? Oh no, it is plus 5. That is a plus 5. This was a minus 5 in the original problem. There are not numbers that multiply to 5 and add to negative 4. And so I think that's our mistake. We're actually going to have to go through and I think do quadratic formula to find our x-intercepts. So we would try to factor this. It doesn't work. And so we're going to have to do quadratic formula. I'm glad you guys are seeing this. So this is a learning opportunity here, right? Everybody can make mistakes. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. All right, x equals 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2a. All right, we have some bad news coming. X equals 4 plus or minus the square root of negative 4 over 2. So that would be x equals 4 plus or minus 2i over 2. And the problem is these x-intercepts, we cannot graph them. There's no way to graph those. They just won't go on a graph because they're imaginary. All right, so let's do this. Since we're sketching the graph, we can skip a step real quick and it's going to help us to sketch the graph. We know that this is our axis of symmetry. And we haven't actually done this with other problems, but if we look at it, if we looked at these points, if it goes over one here, it's got to go over one here to get that next point because it's symmetric, right? That's the axis of symmetry. That means it is symmetric across that line. Same thing here. If I went over 2 to get to that point, I went over 2 to get to that point. So here's what we can do in our new graph. Since we have our axis of symmetry and we have some points, this one is 1, 2 over to get to that point. I can go 2 this way. That means I have to go 2 that way to make it symmetric, right? That's going to make our graph symmetric. And we could check that point if we wanted. If we just didn't feel like we had enough points to graph this, what we could do is just go and make a t-chart and start subbing in values. And what you would do is you would notice if you subbed in a 4, 1, 2, 3, 4 for x, you would get out a negative 5 for y. If you subbed it back into your original problem, you would get out a negative 5. And that is that point right there. You can sub in any numbers that you want. It's just helpful to keep on plugging in numbers until you get something that makes it look like a parabola, right? All right, this one actually has a maximum value, and that maximum value is at 2, negative 1. The domain, as always, is from negative infinity to infinity. And the range is from negative infinity, right? It'll go all the way down, negative infinity, but it does not go all the way up. It stops there at negative 1. It stops at negative 1. All right, I'm sorry about these problems on this one. The x-intercept really threw me for a loop. I thought I saw a pattern that I didn't, right? I thought that we had something was factorable. I tried to factor it, and my factoring was wrong because I had a number incorrect up here. All right, let's keep carrying on. Given the quadratic, all right, so here's another neat little tidbit. So we could have sort of stopped. What I was realizing all the way back here was that as soon as you start to realize that that number is a negative, you know you're not going to be able to plot those points because you're going to get an imaginary number, right? And so that tells us how many solutions we are going to be able to graph. That's how many x-intercepts we're going to have, how many solutions it has, is based on this number that's in here. The number that's in there is b squared minus 4ac. And so what we can do is we could just take b squared minus 4ac and compare it and see how many solutions we're going to have. If the b squared minus 4ac, if that part turns out to be 0, you're going to have exactly one x-intercept. If it's bigger than 0, you're going to have exactly 2 x-intercepts. And if it's less than 0, like on our last problem, right, it turned out to be less than 0, negative number, then you're going to have no x-intercepts, which is exactly what we had, right? All right, so let's try this one. If we did b squared minus 4ac, b squared minus 4ac, it's going to tell us how many x-intercepts we have. So that would be 12 squared minus 4 times 3 times 5. That would be 144 minus 60, and that would be 84. Is that equal to 0, greater than 0, or less than 0? In this case, since it's greater than 0, we have 2 x-intercepts. 2 x-intercepts. It doesn't tell us what they are, but it does tell us whether we need to keep on going and actually find them, right? So it's keeping us from having to do the quadratic formula. On the second one, if we do b squared minus 4ac, that's our numbers. This is it simplified. We get negative 4, and that tells us we have no x-intercepts. All right, now we're on to the application section of this. I talked earlier about a quadratic is used for projectile motion. One example of projectile motion is tossing a ball in the air because it's going to follow that arc. Throwing anything is going to follow that arc. If you threw a rock, if you launched a spaceship, right, and you knew that the spaceship was being held by gravity, that's going to be projectile motion. Any of those types of things where something is being affected by gravity is projectile motion. A stone's thrown from a 100-meter cliff. It gives you all this information at the beginning, an initial speed of 20 meters per second, an angle of 30 degrees from the horizontal. That's a lot of information, isn't it? The height of the stone can be modeled by, here's the good news, it's going to give you the equation where h is the height and t is the time. We want to determine the time at which the stone will reach its maximum height. Remember earlier, we were talking about a maximum height is going to be the vertex, and since that's a negative a, this is going to be facing downwards. We know it's going to have a maximum because it's going to be facing downwards because a is negative. So the maximum height, what we need to do is this, x, y. To find the x, we'll just do negative b over 2a. That would be negative 10 over 2 times negative 4.9. And we need to type that in the calculator. Negative 10 divided by parentheses 2 times negative 4.9. I put the entire denominator in a parentheses there so that the calculator doesn't get confused. And so my x value here is 1.0204, dot, dot, dot. I'm just going to keep that number in my calculator. All right, to find the actual maximum height, that's going to be the y value, right? So if we're looking at this on a graph, x, y, the height that it reaches is the y value. Let's find the y value. To find the y value, we just need to take this number, x, and sub it back into our original equation. So that would be h, 1.0204, I'm keeping the decimal in my calculator, equals negative 4.9 times 1.02 squared plus 10 times 1.02 plus 100. All right, I'm typing that in now. Negative 4.9 times my answer squared plus 10 times my answer plus 100. And I get 105.102. This did say to round to 2 decimal places. I could have chopped off a little bit of that, but now I have 105.10. 105.10. 105.10 is my maximum height. Determine the time at which it will reach its maximum height. Remember, this is h of t, not h of x, and really our x, right, is t. Really, this variable is t representing that. And so our time that it reaches that is 1.02. The time is 1.02. The maximum height rounded to the nearest meter is 105. Time, height. The last part here, determine the time at which the stone will hit the ground. What information do you know? If a stone has hit the ground, right? If a stone goes in the air and hits the ground, if we sort of analyze that, when it hits the ground, that means it hits the x-axis. That means we're looking for an x-intercept. If we could find an x-intercept, we can find where it hits the ground, an x-intercept. To find an x-intercept, we sub a 0 in for y. We could do negative b over 2a to make sure that this is going to work out nicely, but this should give us 2 x-intercepts. To find them, we need to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Whenever I do this calculation, I prefer to do this part first, the inside part first here. That's going to make sure that you don't mess something up in this quadratic formula. So in my calculator, I'm typing 10 squared minus 4 times negative 4.9 times 100. And that gives me 2,060. And 2 times negative 4.9 is negative 9.8. Now I can type the whole thing in my calculator. I'm getting two answers, right? One of them I'm typing a plus in my calculator. The other time I'm typing a minus in my calculator to get both the answers. So negative 10 plus the square root of 2060. I need to put the entire numerator in parentheses, divided by negative 9.8. I'm saying when I type in my calculator, I'm putting the whole top in parentheses. And I get negative 3.61. Remember, we're solving for x, which is the same as t. That's a time. Does time equals negative 3.61 make sense? Time equals negative 3 seconds. No, that doesn't really make sense. So let's do it again. We did it once with the plus. Let's do it with the minus. Typing that in, I get time equals positive 5.65. And that time does make sense. A positive time does make sense. That's the time at which the stone will hit the ground. That is our x-intercept. All right, here's an example. I wish you would pause your video here and try this example out. Again, it gives you all of this initial information about the football, the velocity, the angle, but then it actually just gives you the equation. So all that stuff up top is just saying, this is the equation for what it's actually doing. If we want to find the vertex, that means we're trying to find the maximum height, we're trying to find the vertex. And here's the work for that. Again, you do negative b over 2a to find the x. You sub that into your function to find the y. Find the maximum height of the ball. That is the y value of that. Determine the amount of time to reach the receiver's hand if he catches it at 3 feet off of the ground. That is your height. That means h is 3. So when we go and try and solve that, we're trying to solve for 3, not 0. It's not making it all the way to 0 feet. It's making it to 3 feet. In this last one, if you look at it, we were solving trying to get it to 0 feet off the ground. Here, we're trying to get it 3 feet off the ground. Move the 3 over. Do the quadratic formula. Again, we get two answers, and the only one that makes sense is the 2.05. The negative 0.15 seconds does not make sense. A parking area is to be constructed adjacent to a road. The developer has purchased 340 feet of fencing. So I have set up here, it's adjacent to a road. We don't need fencing on that side. All we need is fencing on these sides for the parking lot, right? They need to be able to pull into the parking lot. He doesn't need fencing on that top side. So all of the fencing adds up to 340 total feet. That means x plus y equals 340 feet. Determine the dimensions of the parking lot that would maximize the area. Maximize. When I see the words maximize, I'm thinking maximum, which makes me think vertex. Anytime we're trying to find the maximum or the minimum, we're trying to find the vertex. If area of a rectangle is length times width, for us that's x times y. And for us to be able to solve this, we're sort of solving this as a system of equations with substitution. If we knew what y was, then we could sub it in to our equation. So here, I know that 2x plus y equals 340. And if I subtract the 2x from both sides, then y equals negative 2x plus 340. That is what y is equal to, and that's what I'm going to sub in for y over here. So our area is x times negative 2x plus 340. And if I distribute, I get our area is negative 2x squared plus 340x. If I want to maximize the area, that means I want to find the vertex of this, right? And so what I'm going to do to find the vertex is negative b over 2a. That would be negative 340 over 2 times negative 2. So that would be, this again is our x, right? That would be negative 340 over negative 4. Negative 340 over negative 4, which is 85. All right, we found our x. X is 85. We have to go in two sort of directions here, right? We have a right equation and a left equation. If we use this right equation, that'll give us y. It asks first for what are the dimensions. The dimensions are x and y. We have the x dimension is 85. We don't have the y dimension, but we can find it by subbing in 85 here. I can type that in my calculator. Negative 2 times 85 plus 340 gives me 170. Y equals 170. And we can sort of do just a check here to make sure that our answers make sense. If this was 85, that was 85, and that's 170, do those add up to our 340 feet of fencing? Yes, they do. If I add those in the calculator, they do add to 340 feet. And then it says find the maximum area. Remember, area is just x times y. So our area is just 85 times 170. And so if I type that number in my calculator, 85 times 170 gives me 14,450. This is all in feet. So this is 85 feet. This is 170 feet. And this is 14,450 square feet. One more example here. A farmer has 200 feet of fencing. Very similar problem. He wants to build 3 adjacent rectangular corrals. So we're going to have to cover all 4 of those sides with fencing. Determine the dimensions to maximize the area. Area is still just length times width, right? So area is still just x times y. Pause the video and see if you could figure this out. I set up the 240 feet of fencing to be total of all of those items, the x, 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 y, y. Then I combined all the like terms, 4 x's, 2 y's, and continued to try to solve for y. With a known y, we can sub that into this original equation. Simplify on the right side. If we want to maximize, that means we want to find the vertex. If you do negative b over 2a, it gives you 25. If you sub that 25 back into your original equation, it gives you 1250, which is your area. If we want to know what y is, because it does say determine the dimensions, right? Determine the dimensions to maximize and find the area. We've got the area. The area is done. We've got the x part of the dimensions. To find the y part of the dimensions, I can just sub an x into my y part. Negative 2 times 25 plus 100, and get 50. So the dimensions I have highlighted in yellow, and I can circle my area in red. It's a 25 by 50 panel. 25 times 50 is 1250, and we could just check just to make sure that if we did 25, 25, 25, 25, 50, and 50, those do add up to a total of 200 feet of fencing.